concepts that some of us read about last night that we're actually learning a whole lot more about today. So some of us have a lot to share that are regarding solutions and concentrations and something called colligative properties. Others of us have more to share about boiling point and phase changes. So someplace, either if you have space on the paper you were writing on, like your reflection and your summary, then we're just going to make 3 little blocks for me. Call it out as salty roads, which is what one of the articles is. One's about Yellowstone geysers, and the other's about the Flint water crisis. So just make like a 3 little box system, and in those boxes, whenever everybody's sharing, you're going to just write down something that's chemically significant. So like relating that to chemistry. So chemically significant, and that's just 2 bullet points of chemical significance per article, including your own. So if you want to go ahead and start with your own, that might give you a little bit more context to share about. So I used to have 4 articles, that's why there's a blank 4th square. So go ahead and write down 2 chemically significant thoughts about your region. Take you terribly long since you read yours. Finish that thought you're writing, and if you are Flint water crisis, you're going to stand up over here in the corner. If you're the geysers, you're going to stand up in your New Year's table, and if you're salty road, you're going to kind of stand up those area back here. Flint water, geysers over there, salty roads to the back. Number yourselves off, 1 through whatever. Yep. Okay, we're looking first here. Alright, we should have a bowed even number, so go ahead and number yourselves off. 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's not see you kind of know where you're heading, okay? 1s, right here, 2s, 3s, 4s, 5s, 6s, etc. in the front. So 7, 8, 9 will be like the front. Wait, what should be a group of 3 with 3 different articles? 1, 2, 3.
What about my 7? Where's my 7?
Alright, guys in the front, you're going to have to find a place to sit down. Find a place to sit down. Alright, so I want you guys to start with just sharing the premise of the article, the summary. It doesn't have to be literally your summary, but tell them some stuff about what you read, and then give them some chemical significances that they can provide and write it down. Okay? Everybody's doing groups of 3, and whoever wants to start can go from the beginning. Okay, Audrey.
Yeah.
Okay. Thank you.
Salt is used to minimize wording on roadways or is used to minimize So adding salt to water will lower the freezing point, so that's what prevents the ice from freezing. This can also be used to purify water because the coolest solution enough, the ice crystals that start to form are made of like the pure frozen water, so all the salt is pushed out essentially. Let's see. This also prevents like the ice in the stove from actually sticking to the pigment, so it's easier when the flowers come. So you can easily move it out of the way. This does have some environmental effects with the salts. It causes like corrosion and stuff, but they're working on other like alternative salts, like a magnesium chloride salt that they can use instead that could potentially be more effective and also a little more environmentally friendly. That's pretty much it. Unless you have something to add.
Take about one more minute to share.
We're looking at Bailey's face.
Come back to your seats. And you're walking. And you're walking. All right, so I'm going to ask for a chemical significance from a couple of you guys, and then we'll turn those in, okay? Elizabeth, give me any chemical significance of any article. Okay, so 2 different types of salts are used to make rock salts for the salts on the roads. CJ?
So in the geysers, once you send out water, it reaches 300 degrees Celsius, but it stays in the liquid form because of the pressure of the rock.
Right, so that's us thinking back to phase diagrams, how pressure can stop a phase change from occurring to the point where 300 degrees Celsius water should have been gas, but it's not. Who's ever been to a hot spring? Seen a hot spring? Yellowstone is what the article is mainly about, but yeah, people die in there because people are stupid and they get in the water. They think it's always like a hot tub. No, they dissolve, and all they find are their like keys and wallets. It happened last year. It gets pretty dang hot. Kern, tell me something.
Water over time oxidize the pipe holder and rust.
Good. So oxidation is a really good term for that. So talking about how some water is going to have different chemicals in it, which would affect the pipes. Who else had the pipes from the Flint water crisis? Tell me more.
So corrosion on the pipes leads to like lead from like the pipes are made of lead, and so lead from the pipes after they're corroded goes into the water.
Right. And what happens when lead goes into water, Maverick?
Yeah, causes burns.
Yeah, and if you guys have never watched like a documentary, like a YouTube video on like people's testimonies from the Flint water crisis from a couple years ago, it's like devastating. It's like heartbreaking to hear that basically they changed the water supply from, you know, Lake A to Lake B. Well, Lake B had a different chemical, like water chemistry to it, and so it was flowing through the pipes and had unintended consequences. And then Michigan was like, we didn't know, and then they still didn't do anything for a while, and their citizens were like really in a lot of hardship. So very good, and we will talk more about the salty roads today. Okay, so the salty roads are our like main topic today. It's called colligative properties. If you would send one of your people in your pod to go put that in the box, and then everybody else is drawing. Okay. So, I don't care if you send them to stick it in the box. Yeah, if you need a staple, then staple. You have a minute to put in the box right now. Otherwise, everyone's drawing what's on the board. You guys can bring the stapler that way too, since it's right in front of the board. No staples?
No.
I'm always out. How am I always out? Always. All right, thank you. All right, you're doing a quick sketch here. I want you to think about how these different substances could interact with water, how they would dissolve differently with water. Some of us are going to identify up front that we have a series of combinations of ionic and covalent. Which of these three are covalent? 1, 2, or 3?
3.
Why 3? It has only nonmetals, and we know there's no polyatomic ions involved. That is not a hydroxide, that's an alcohol group. And you actually can see it kind of with the structure here, CC, H, H, H. I cut off part of the other H. O, O, and then that's an OH. So this is all covalent. So I'm going to start with this one. What happens when it goes in water? Does it dissolve? Dissolve is a really just non-descriptive term. Dissolve can mean it goes in water and it literally breaks apart into ions. Dissolve can mean it goes into water and water just surrounds it. It means it goes and it kind of disappears. Does sugar dissolve in water? Yeah, like we make sweet tea all the time. We live in the South. So this, just think of this as sugar. Sugar is a covalent compound. This is ethanol, which is an alcohol product. That's also a covalent compound. But what happens is this just goes into the solution as a whole molecule, and then water just surrounds it. So the word dissolve is basically useless to us unless we want more, specifically we want more information. So water is just surrounding it, right? So I'm going to call that word hydrate. It's kind of like water surrounding something. Is it breaking up any of the bonded structure in here? Yeah or nay?
No.
No. So I put 1 molecule in, I still have 1 molecule. I put 10 molecules in, I still have 10 molecules. There's been no changes whatsoever. What happens when I put, are these ionic or covalent? They're definitely ionic. Well, ionic things act very differently in water. What do? Don't say the word dissolve again, because that's really not a great term. Anybody have a term for that? So what's the word that means that ionic compounds break apart? It's going to be give us a lot of information. Starts in the I. Ionize, right? So these are going to ionize. That's the term we should use for that. So when sodium bromide goes into water, what does it make? Well, give me specifics. When sodium bromide goes into water, you guys are telling me it ionizes, which Jacob said that means break apart. So what 2 things does it break apart into? Na what? Na what? It's an ion. Come on, guys. Na plus, right? It's the cation, sodium, and who's the other? Br minus. It's just the ion or the anion bromide. So they're broken apart. I know I have them touching here, but they're definitely broken apart. And so I put 1 ionic structure in, and how many ions do I provide? Or how many ions do I get? 2. Okay, so that's important. We put covalent things in, we put 1 thing in, we get 1 thing out. There's been no change of number. We put an ionic structure in, happens to have 2 ions, we get 2 ions out. You hopefully can get my flow here. Draw the next one. So name this for me too. Out loud, people, let's go. Calcium chloride. Okay, so what does calcium chloride ionize into? Ca2 plus and Cl1 minus and Cl1 minus, because there are 2 of them. So we have how many ions produced? 3. So another term other than ionize that you might see like in some of your homework would be the word dissociate. Dissociate means that it if you have a friend and your friend is being mean to you and you're like, whatever, I'm not going to associate with them anymore, you have dissociated. You have broken apart from them. So dissociate means just not to associate, so they pull apart. But in the end, we get 3 ions out of this. What we've discovered is that different compounds behave differently in water, specifically water here, and they make a number of ions that would differ than what we put in there. This one's going to only have 1 molecule remaining because it's molecular. There's no ionization present. That's going to be important here in about 5 minutes, okay? Give me a thumbs up if I can move on. Okay, so we have to know how to dissociate something. Okay, of these substances, sodium bromide, calcium chloride, and ethanol, which of them would you consider electrolytes? Talking group first, maybe? Take 30 seconds. All right, Corbin's table, what do you guys think? Who's going to be classified as an electrolyte?
The first 2.
Okay, which were? Okay, so we're going to put example, electrolytes, sodium bromide, and calcium chloride. Why did you select those? Hold on. Chandler's table, why would we have selected those?
Because they're ionic.
Good. Only the ionic substances will make ions. Okay? So the fact that something's ionic, when it goes into water, it should make ions, at least to a small extent. Why are they called electrolytes? I got that table. Aiden's table. My bad. Anushka's table. Why do we want to term ions as electrolytes? What does electrolyte mean? Like the definition. What is it able to do? Say again? Right. Electrolytes are simply something that's able to conduct electricity. And there should be a reason why why we consider ions able to do that. Can you guys talk in your groups first and talk about why ions are able to do that? Talk in your groups first. All right, Bryce the table. What do you guys think? Why are ions able to conduct electricity? Okay, it does have something to do with their charges. So I will elaborate there. If we have a bunch of positives and negatives hanging out in this solution because it's an ionic solution, what happens is this battery is providing electricity. What is electricity made up of again? Just straight electrons. That's it, right? So electrons are traveling through the battery. They actually come out of this terminal. They travel down this little rod, and then the electrons are able to bounce between all these ionic charges because they're negatively charged, and so they are technically kind of like an ion. They are a charge. So they bounce, they bounce to this other terminal, and they can flow through the wire, and then because the circuit is complete, there's a complete circuit of conductive stuff, the light bulb will come on. So we need to know that ionics are definitely electrolytes. So then everything else that's non-ionic technically should be a non-electrolyte. And the example we had earlier, what was it? Ethanol. Okay, so does this make ions? Everybody, yay or nay? No ions? And if you can't make ions, then you're not going to be able to conduct electricity. If you cannot conduct electricity, the battery would shoot its electrons out to the side, right? It'd come down here, and the electrons get stuck because there's no way for it to bounce around to the other terminal, to the other side. So is this a complete circuit? Good. Incomplete. Okay. So that's a quick talk on electrolytes. You can easily tell something's an electrolyte specifically if it's ionic and it's in solution. All right, so now the real topic of the day, colligative properties. I'm going to be quiet for a minute. This is kind of our biggest slide on content, and then we have another one with the mathematics behind it, and we're going to practice on it. Bottom with the vapor pressure is a reminder. You may not remember the definition of vapor pressure, so I want to provide it. come right back down. In just a second. Okay, so the big term is colligative properties. Just like any property, like if you think of physical properties of everyday substances, they all have a very specific boiling point, they have a specific freezing point, melting point, etc. Color, viscosity, surface tension, like everything has physical properties. But pure solvents, like what's our favorite solvent we use all the time? Water. Pure solvents are just whatever the solvent's property is. They have a physical property. So for water, what are some of the physical properties we know of water? What's the freezing point of water? 0 degrees Celsius. What's the boiling point of water? 100 degrees Celsius. But the moment we take water and we add a solute to it, what do we have now? Okay, so we have a solution, technically, right? So that solution has different properties than the pure solvent originally had. So upon adding solutes, we now call these solution properties colligative properties. It's just the name for it. So obviously, if water boils at 100 degrees Celsius, if I add a solute, it's going to vary or change the boiling point. It's also going to change the freezing point. It's also going to change the vapor pressure. And the direction that it changes is indicated by the direction here. So you can tell that every single time I make a solution from the pure solvent, what's definitely going to happen to freezing point? It's going to be lowered, because that's what depression means. It means to depress the freezing point. What's definitely going to happen to boiling point every time I make a solution from a pure substance? It's going to go higher. That's what elevation means. It means to go higher. And vapor pressure, of course, would be lowered. So we lower vapor pressure, we'd lower freezing point, and we heighten boiling point upon making this solution. But not every solute acts the same. We just figured that out, right? What do ionic substances do in solutions? Ionize, or the other word? Dissociate. And covalent things do in solution. Hydrate, right? They don't break apart. They just kind of get surrounded by water. So that's why it's important to know how many particles are produced upon that solute going into solution. Once we know that information, we can then do the math with it, which is actually how much the freezing point depresses or how much the boiling point elevates and so forth. So this is going to help us with calculations. Okay? The specific identity doesn't matter. Like, it doesn't matter if it's ethanol or methanol or heptanol or octanol. It's the fact that does it break up or does it not. Thumbs up? Okay. These are all called what properties? Colligative properties. Good. Okay, so freezing point lowering is not one we will calculate with, but we just have to understand why it occurs. So in this, who was my atmospheric pressure? Is it Bryce? Bryce, you were my atmospheric pressure. So whenever I was the boiling water and you were trying to press back down, so the idea is that when vapor pressure, which is the vapor pressure of the liquid, equals the atmospheric pressure, they are fighting against each other. So the atmospheric pressure is pushing down, the vapor pressure is pushing up. So at that point, that's when it will boil. Well, this is all pure substance, right? This blue stuff is just like pure water, for example. What does pure water start to do with, let's say, so you see the positive charges all throughout? Let's just call that sodium ion. Maybe sodium chloride is present. What does pure water start to do with sodium chloride upon sodium chloride's introduction to it? Talk in your groups first. I got no volunteers yet. So what do these guys do together? Kendall's table, help me out. You can't go wrong. There's really, use your gut. Oh, say again? I'm going to ask for you guys to collaborate one more time because we have like, this is very logical. We've done the lab with this. We've talked about this before. We just talked about it yesterday a little bit. Go. Use your gut.
Like the water basically wraps around each of the ions.
When you say wraps around, what are you trying to tell me it's doing?
It's like surrounding them.
Okay, so water looks like this. And here's sodium ion, right? So keep going, Corbin.
So the partial negatives or positives of the water molecules will interact with the negative
That's
or positive charges.
perfect. All I want you to say is that water would interact with ions. Who was on that brainwave? Water interacts with ions. You gotta read between the lines, people. There's really nothing else water's gonna do. I mean, it could technically react, but it's just gonna ionize again. So water's partial negative and partial positive is gonna play really nicely with the partial or with the full positive and full negative on these ions. So simply, it's going to interact. Okay, and that's probably through some sort of intermolecular force of sorts. So this water is freely just hydrogen bonding with itself, kind of hanging out, and that water is going to vaporize, readily whenever it wishes. Well, what do you think is going to happen to this water if it's interacting with the ions? Is it as readily vaporizing? No, it's hanging out with these ions because it's super magnetically attracted to them. It's not going to vaporize very well. So the vapors are fewer and far between. So what happened to the vapor pressure? So lots of vapors, high or low vapor pressure? High. Vapors, high vapor pressure, right? Because if you have more vapors, there's just more of them, therefore the pressure would be higher. Is this vaporizing? Not as much because it's interacting with ions. So what's happening to vapor pressure? It's lesser, right? It's going down. Hence, vapor pressure lowering. That's the colligative property. Because there's stuff to play with, water doesn't vaporize, water's vapor pressure lowers. Give me a thumbs up if that concept kind of logically makes sense now. It's all about the ions just basically interacting. Okay, the other two are a little bit more math heavy, so we're going to talk about the examples first and then we'll do the math of that. So with freezing point depression, you have the example that we saw in our readings, which are salty roads. We have our lab we're doing tomorrow, which is making ice cream, all through freezing point depression. And then the fact that who drives? Who has ridden in a car? All right, so we all have radiators we have to deal with. What is the job of the radiator in the car? Say, what's the job of the radiator? Anybody? Corbin? Okay, so not only to cool the car down, but just to keep it simply from overheating. What happens if your car overheats? It just breaks down, right? You don't want any kind of radiator issues. So this would go in the radiator, and what would happen is if the car started to overheat, it would heighten the boiling point so much, which is actually more of an example for boiling point elevation, it would stop the water from boiling because boiling water in your radiator would cause a lot of steam and issues within your engine. It also lowers the freezing point of that water, glycol, or whatever's in the radiator, and it's going to stop it from freezing. Because do you think frozen fluids in your car is a good thing? No, things need to kind of move around. So we don't want any frozen water, for example, in our radiator, so we actually put something called antifreeze in it, which is its job is to lower the freezing point, to stop it from freezing. The way this works is, what does water do when it forms ice? We saw a picture of it once. Okay, yes, it expands. What does it geometrically look like when it makes ice? It does make a crystalline lattice. What's the shape of that crystal? Does anybody remember that? I see you making shapes with your hands. I'm not sure what that is. It's a hexagon. Do you guys remember it was a hexagon like this? Yeah, maybe you don't. Okay, so basically water forms a little hexagon, and in that hexagon, it's all attracted to all the other water molecules through what? Hydrogen bonding, right? Key word for water is hydrogen bonding. So what's going to happen is if water wants to do that, it can totally do that on its own. But if there's a bunch of salt or magnesium ions or calcium ions floating around, these ions are all going to attract to water, and they're going to kind of jump in the way, and they're going to stop this process from occurring. So can it crystallize if these are interacting with it? Not well, right? It's going to have to get really, really, really low in temperature, really, really slow in kinetic energy. Because remember, as temperature goes down, kinetic energy goes down. They're going to have to get really slowly moving to the point where they just kind of freeze in motion. And so that's going to be hopefully lower than 0 degrees Celsius. If not, our radiator's antifreeze did not do its job. So basically, all these ions get in the way, and they stop the crystals from forming, or the crystallization process. And if they do that, they should lower the freezing point. They stop the crystallization process. Okay? Oh, and then I thought I would show you this graph. Use my pointer. You can kind of see That's vapor pressure. Oh, never mind. I'll show you the other graph in a second. Okay, so for boiling point, obviously it's the boiling point elevation, so all of these are going to have higher boiling points. Who's ever put salt in their water when like cooking spaghetti or noodles or something? Okay, why do you do that? Okay, so to impart some flavor. To what? Increase. Oh, good. To increase the boiling point, right? What does water normally boil at? 100. And we want it to boil because, like, that's what spaghetti calls for. It wants boiling water. But sometimes it boils so much it starts to overflow, and it's going to make a mess in the stove. So we put salt in there, actually, to heighten the boiling point to maybe like 102, 103 degrees Celsius. And when it does that, our bubbles don't form as fast, the foam doesn't boil up and over the top. And it has an added effect of flavor. Okay? So boiling point elevation is really important in animals and plant life, like out in the desert, because most plant life and animal life has what in the body? Water, right? It gets pretty hot out there, yeah? So if they have water in their body and it gets to 100 degrees Celsius, what could happen to that water? Basically, they would boil to death, right? They would boil. Their body would overheat to the extent that they would die. And cacti have a lot of solutes in their bodies, in their cells, and those solutes heighten the boiling point. So maybe their cells wouldn't boil until, I don't know, 115 degrees Celsius, which is unlikely to we probably won't get that hot. So they're going to be kind of evolutionarily, what's the word I'm looking for? Selected for it, because they're going to have the better chance at survival. So that's really important in animal life and plant life as well. Okay, why does the freezing point depress when we add salts? Okay, so the ions disrupt the hydrogen bonding process and it disrupts the crystallization process. That's really important. The same thing kind of happens here, but it's not crystallization because obviously when we're boiling, we're not crystallizing. It's more related to the fact that it's raising the vapor pressure. Okay, so equations. Let me tell you what's important here. So I do have a couple of things underlined up here which would be important for you to know. We use the word non-volatile to indicate something covalent because we don't want to increase volatility, which is vaporization. So usually if I say non-volatile or a non-electrolyte, you should read in between the lines and realize that it's something covalent. If you have a solute that's covalent, does it dissociate? No. So we're going to call that an I equal to 1. I equal to 1. All right, you should be writing this down. This is not just a watch and learn kind of thing because you're going to want this for reference. Okay? If you have something ionic, it will dissociate. And so our job is to figure out, how many electrolytes does it make. And so we'll have an I of greater than 1. It might be 2, it might be 3, it might be 4, it kind of depends. So I'm going to tell you guys that first, and then we're going to actually get down to what the I value actually stands for. So ions, or ionic compounds make ions, we have a larger number. Covalents don't make ions, we have an I of 1. I'll come right back up to that. So I stands for number of moles of ion, which is also named after a scientist. You know, all scientists like to name some things after themselves. It's called the Van 't Hoff factor. Van 't Hoff factor. Guess who named it? Van 't Hoff, you smart cookies. All right, so I want you to consider the dissociation of each of these ionic species, and I want in your groups you guys come up with the I number, meaning the number of ions they form. Write down those 4 examples and go. You can't read a number I can tell you really small. That one? That's a 3. That's a 3. Alright, I'm going to demonstrate the first one. It's the easier one, but I'll show you how you should think about it, and then you guys can rethink if you need to. I have magnesium chloride, right? Magnesium chloride is technically made up of magnesium 2+ ion and 2 chloride ions, right? Because that's a magnesium 2+, and that chlorine only has a 1- charge, but there's a 2 on the outside because of crisscrossing. But that indicates to me there are 2 of those ions. So there's 1 magnesium and there's 2 chloride ions, which makes an I of 3. Okay, I want you to walk through that same process, but for the rest of them, non-stable first, this aluminum oxide one. Walk through that process. Okay, so when aluminum oxide dissolves or dissociates, it makes 2 aluminum charge 3+ ions, right? And 3 O2- ions, totaling of what? I of 5. Okay, so 2 + 3 is 5. Same process, monostable. Say it louder for me. Okay, so when calcium hydroxide dissolves, it dissociates, makes calcium 2+ and good, 2 hydroxide ions, because hydroxide is a polyatomic ion, it stays together, so we need to keep it together. Total of what? No? There's 1 calcium, right? And there's 2 hydroxides, so 1 + 2 is 3. Where do we get 5? Because I saw that on like a couple of y'all's papers. Oh. Yeah, we want to keep that OH together because it is a polyatomic. So that's an I of 3. Next table, up here, Ariel's table. Calcium carbonate, what happens when it dissociates? Okay, so we make a Ca2+, because that's the ion calcium, and all right, talk in your groups first. See if you can come to a conclusion. You have 30 seconds. All right, come back to me. Is CO3 going to stay together, or is it going to break apart? Raise your hand on stay together. Raise your hand on break apart. Okay, we all agreed that calcium is its own entity, and carbonate is technically CO3 2-. That's carbonate. That's a polyatomic. So what does this break into? How many ions? How many? 1 more time. I keep hearing 3. It's 2. There's 1 calcium and there's 1 carbonate. Right? There's no O that's separating at all. It's staying with the C. So this is an I of 2. Basically, you think about how did I get this together? I just took 2 ions and put them together, and those 2 + 2 negative charges reduced down. Kind of old school, like nomenclature stuff, actually. Okay, so we have to know how ions are going to break, or ionic compounds are going to break down before we can apply the concepts. Can I move back up now? A little bit? Okay. So we will use the I constant, the I value, in the equation. So it looks like there's a lot of equations, but really there's only one. The general formula is the one I would write down, because what you'll notice is that it applies to both situations the same. So delta T is going to be, obviously, change in temperature, okay, and if we are measuring this in Celsius, and that might remind you a little bit of like the MCAT stuff. K is a little k, and that means Malau constant. And it could be a freezing point constant or a boiling point constant. So it depends on the situation. If it's asking about boiling point stuff, we use the correct boiling point constant. If it's asking about freezing point stuff, we use the correct freezing point constant. Two very common ones that we'll use are for water, and in your textbook, you can find the whole list of them on page 494 and 495. But for water, we use KFP. What do you think the FP stands for? Freezing point. We use 1.86 degrees C per millal. What's the M stand for? Millal, which is related to molality, right? Not molarity, molality. Okay, so that's our freezing point constant for water. And then 0.512 degrees C per millal is our boiling point constant for water. So water is our solvent here in the case that we would be using these constants. So water would be the solvent. Okay, so in the equation, check, we know delta T stands for change in temperature, K stands for millal, freezing point or boiling point constant, I stands for number of moles of ions, or if it's covalent compound, what's always I? 1. And then what's the little m stand for? Molality. Right. Reminder, what's molality's unit? Moles of solute over, I'm supposed to say kilogram of solvent. The one we use often, you write as water as our solvent, but I could give you other solvents, correct? Like totally good. Okay. All right, so notice that these are all just Chem. Delta T is equal to Chem. Got it? So think of a lady named Kim every time you think of this one. Can I move on? Delta T is equal to Chem. Delta T is equal to Chem. Okay. I'm going to go to a problem first. Okay, so question 1. How much will adding 2.65 moles of sugar decrease the freezing point of 2.5 kilograms of water? How will it change the boiling point? What will the new freezing point and new boiling point be? All right, so there's like 4 questions here. We're going to tackle the first one together. If I'm looking at anything regarding freezing point and boiling point, it's talking about changes, what equation comes to mind? Say again? Chem. Delta T is equal to Chem. So the first thing when I read this question, I'm like, okay, this is a colligative property question I must calculate, so I have to have delta T is equal to Chem. K is going to be referencing, let's do the freezing point one first, right? And what is this sugar going into? It's going into water, right? So I must use the K value for water, right? And since I'm doing freezing point first, I'm going to put KFP right there. What's the, notice it says, how much will it decrease the freezing point? So which of these is my question? Which variable here is my question? Temperature, right? So delta T is my question. KFP is what? You just write this down. 1.86 degrees C per millal. What's the I factor for this particular question? Good, this is 1. Notice the I factor must be regarding the covalent solute. The I always talks about the solute, for K always talks about the solvent. Okay? The I is 1. And what's the M? So it's not explicitly provided, right? So what do we have to do? Calculate it, okay? If you need a calculator, go grab one, but let's keep rolling, okay? Molality, we need to calculate. Guys, get up and I'm moving, okay? It's already 9:44, and I'd like to have you finish this in class. All right, guys, tell me how I'm getting molality. 2.65 moles of solute divided by what? 2.5 kilograms of water. Okay, what is that molality? 1.06. Okay, we know we're looking for delta T for the freezing point difference. We're looking at each of these values provided to us. All of this is going to get plugged in together. Delta T is equal to KFP IM. K is 1.86 degrees C per millal. I is 1 for the covalent sugar molecule because it's not going to dissociate, and M is 1.06 millal. What unit cancels? Malal. Okay, what unit remains? Celsius, which it should be that because we're looking at temperature change. Can you guys tell me that? 1.9. I'm gonna stop there. Okay. So this is our temperature change. That's our delta T. That's the freezing point depression. So decide in your groups what's the new freezing point of this solution. You have 30 seconds. What's the new freezing point of this solution? Think about where we started and how it would be depressed. Dunn's table. What's the new freezing point? Perfect. Tell me your logic there.
Water's original freezing point is zero.
Okay? So we're depressing it, so we're subtracting it, okay? And we're subtracting the delta T, correct? Perfect. So that's your thought process. Original freezing point, 0 for water. Depress it by 1.97, gives us a new freezing point of negative 1.97 degrees Celsius. Perfect. Now you guys do boiling point. So we did the freezing point one. It's all the same scenario, except your boiling point constant will change. All right, give me a table. Tell me how you're picking up on this one. Okay, so we're changing. So it's still delta T is equal to KIM, right? But we're using the boiling point constant. Is that what you're saying? Okay, what's that boiling point constant? 0.512 degrees C per millal. What's the I value? Still 1 because it's still sugar. What's the M value? Still the same concentration. All right, what is our final temperature change here? Hold on, I got you. I'm still working with community table. 0.542. Okay. All right, talk in your groups. You have 10 seconds. What's the new boiling point of this solution? All right, Aiden's table. New boiling point.
100.542.
Good. New boiling point is going to be the original, which was what?
100.
Good, because we are dealing with water, so the original boiling point of water is 100 plus, so it's elevated, boiling point elevation of 0.542, and that should be 100.542. I know it wasn't very much, but it did raise the boiling point, okay? You got to know the directions. It's freezing point depression, boiling point elevation. All right, similar scenario. Can I scroll down? Similar scenario. Oh, darn it. Somehow blended. Number 2. Write down your equation. Write down your calculations. A lot of naked numbers. Let's get some units on those puppies. Which comes up if you have your new freezing point. Okay, you got your new boiling point? About half this are there, okay? If you are ready, you can proceed down to 3, and I'll scroll up to 4 in just a second. So your freezing point, did anybody notice the relationship between question 1 and 2? What was the relationship? Okay, so I hear a lot of the same data, but what's the relationship between the new freezing points? Why is it doubled? Why was the sodium chloride doubled? You have how many more ions? Well, the ratio. So really, the thing that matters is the I factor. The fact that sodium chloride had a Van 't Hoff factor of 2 versus the sugar of 1 made our whole situation just double the delta T, which significantly decreased the freezing point, and of course doubled the boiling point elevation as well. So the idea is that I factor will matter, and that's sometimes the only thing you need to look at. So 3, which has a greater effect, sugar or salt. For sure, salt, anything ionic will have a greater impact on all the colligative properties, elevation or depression, okay? And then you guys talk about these. Which of these will change the boiling point the most and the least? So write down your formulas. I would think that would be better. Go ahead, Manal. And pull out your lecture notes from yesterday too, so we can get back on that. Hannah's table, give me one of these formulas here. Good. Carbon tetrachloride, CCl4. Bradley's table, another. NaCl, and then Bailey's table, the other. Al. Al2. O3. Good. Okay. Which of these is going to impact the boiling point the most? Everybody. Which one? Okay. So basically, we need to figure out the what for all of these. I. What's the I factor up here on the first one? 1. It's covalent. It doesn't do anything. 2. Last one. 5. We actually just did that example, right? So the I factor of 5 is going to cause the greatest change in boiling point. Who's going to have the least? Who's going to have the least? Number 1, right, calcium tetrachloride. All right, and now you guys can find your lecture notes. There are a series of 8 questions. It's lecture problems to colligative properties, and you guys are going to process these 8 questions in about 20 minutes, okay? And then after that, you will finish up PS 15, 16. What I do need to give you, and so this is on your paper, yes? Make sure you find it. It's in the lower, thank you, lower right side below the 1 through 18. I do need to give you the other solvent K values. You don't need to write these down though. Whenever you find that you're not working with water as your solvent, you need to use a different K value. So I've got everything from acetic acid to benzene to camphor and whatnot. And the ones over here on the left side are KF, freezing point. The ones on the right are KB for boiling point. And I have the answers here we can check after a little bit, okay? So working your table groups, if you have the table not, write it down. Okay, that's where you're going. Show your units and show your work. After I see that you're done, I'm just going to give you credit for 1 through 8. So only if you're working with something other than water do you really need the board.